So what am I supposed to do now? Okay. Well, the end of the semester is coming. We are going towards the end of the semester. So I'm getting more and more pressed to end up what I wanted to teach. So today I will continue what we started last time, meaning Laplace integrals, or the general topic of asymptotics of integrals. And then we can move to two-time perturbation theory. How much we will be able to do, that's a good question. Okay. So let's okay, so just to remind you, what was the main idea? The main idea is that if I have an integral from a to b on f of t e to the x phi of t dt, that's the integral, and I want to estimate this integral at the limit x goes to infinity, then I want to take the place where phi has a maximum. And this was the basis for the expansion we have described last time. Okay? Okay, so to begin, right. So to begin, let's speak about the integral, something which is simpler. The integral from 0 to infinity of f of t times e to the minus x t dt. Okay? Now, what is the solution for this integral? That's a good question. However, if I'm interested in the asymptotics of this integral when x is very large, then I know that the main contribution will come from the vicinity of 0, unless f is doing something horrible at the vicinity of 0. So let's for the moment assume that f is not doing something horrible at the vicinity of 0, which implies that we assume that f of t may be written as, okay, not necessarily as a Taylor series, it may be more general than a Taylor series, but something that may be written in some form of a power series. i.e., I assume that f of t may be written as t to the power of alpha, sum from n equals 0 to infinity of an t to the power of n beta. So the powers may not be integers, and we may have some coefficient here that it may be t to the minus 1/2, so it may blow up at 0, doesn't matter, right? We assume that f of t is nice enough to be such that we can represent it by this series, right? This is not a Taylor series, okay? This is much more general than a Taylor series. Okay?
Because of the beta?
Because of the beta and because of the alpha.
Mm-hmm.
So as long as we can write f in that form, now we can write this integral as the sum from n equals 0 to infinity of an, and now we have the integral from 0 to infinity of t to the alpha plus n beta e to the minus x t dt. Have I forgotten something? No, that's it. You agree?
Yes.
Now, this may be written as sum from n equals 0 to infinity. Now let's define q as xt. So dt is dq over x, right? So what I will have here is an, and now I will take out of the integral the x things. So I will have, let's write it as an divided by x. So first of all I have this x, because now I have an integral dq, again from 0 to infinity, but I have here x, right? And then I'm writing this as q to the power of alpha plus n beta, e to the minus q dq. Okay, the dq is already written. So what is missing here is the x. So here I have x to the alpha plus n beta plus 1. Do you see that? Good. And what is this? Gamma function. That's a gamma function. This is a gamma function of alpha plus n beta plus 1. So, at the end of the day, what we have gotten? We have gotten the sum from n equals 0 to infinity of an gamma of alpha plus n beta plus 1 divided by x to the alpha plus n beta plus 1. That's it. Right? So this is a power series for the integral. And as you see, we have here all the power series in inverse powers of x. So if you want the approximation, the leading approximation will be the first term. As x goes to infinity, right, you can write it, no problems.
I
What?
don't understand. Why do we want this?
Why do we want this? What does it mean? That's a great thing. It's an expansion of this integral. As x goes to infinity, it gives you an expansion of the integral.
Why do you want the solution as expansion of? I didn't understand. Why do you want?
This is what we are. This is the topic of this part of the course, right? You have an integral that depends on a parameter.
Yes.
The parameter is x, and now we want to understand what the asymptotics of the integral. Okay, this is an asymptotic series. This is not Taylor series. But now you have the full asymptotic series of the integral. So the formula is saying that if you have this integral, the full asymptotic expansion of this integral is sum from n equals 0 to infinity of an that I've taken from here, right? Gamma of alpha plus beta n plus 1 divided by x to alpha plus beta n plus 1. Right? And this is such an important formula that it has a name. It's called Watson lemma. Yeah. It's not a guy from Sherlock Holmes, but this is Watson's lemma. So let's provide one example at least for Watson's lemma. What's the example I want to take? Yes, so the integral from 0 to 5 of, I want the integral is the integral from 0 to 5 of e to the minus xt divided by 1 plus t squared. Right? This is just, it's very easy, but it's just to show you what we are speaking about. Okay? You see? I want to expand this dt. Yes. And I want to ask what is the what is the expansion of this as x goes to infinity? The answer is, all I have to do is to write f of t in that form.
Yeah, but the upper limit is 5, not infinity.
That's right. This
But
is
it's 5,
integral.
less than 5, it's really
It's the
small,
integral.
so it doesn't contribute
Wait,
much
wait,
to the
wait.
integral.
Okay. Let's continue. Right. So what we are doing is we are writing 1 over 1 plus t squared. This is the sum from n equals 0 to infinity of minus 1 to the power of n t to the power of 2n. Yes? Just expansion. And we put it here. So, I mean, okay, we can use it in the formula, right? So, an, so how do I translate it to this canonical form? I will take alpha to be 1,
0.
0, alpha is 0.
Beta is
I will take beta to be 2, and I will take an to be minus 1 to the power of n, right? Is that correct?
Yes.
Okay? And what I will get here is sum from n equals 0 to infinity of minus 1 to the power of n. Here I have gamma of 0 plus 2n plus 1. That's 2n plus 1, 2n factorial, right? Divided by
x to the 2n.
x to the
2n plus 1.
2n plus 1. Which means that what are the results for n equals 0?
Undefined. For n equal to 0.
For n equals to 0, I have 1 over x. And then I have minus, if n is 1, I have minus, this is 2 over x cubed. And now I have plus, n is 2. So here I have 4 factorial divided by x to the 5 minus blah blah blah. Okay, this is what I get from Watson's lemma. Now, who asked that? This is from 0 to 5, not from 0 to infinity.
But the function declines so fast.
The answer is, who cares? At the limit x goes to infinity, everything that goes from 5 to infinity is subdominant. Is exponentially small in x. So we can neglect it with regard to any power. Right? So this is true no matter what is the upper what's the upper bound of this integral. Right? So every upper bound, it will give the same 15, whatever.
So like
It
0
will
to
give, it
epsilon.
has the same expansion.
So like 0 to epsilon for every epsilon, positive epsilon?
Yes. Yes. As x goes to infinity.
Yes.
Right? So you see the point. Summing up all these terms, if you can sum them up, it will give you still an asymptotic formula because you still miss everything between 15 or between 5 and infinity. Okay? Good. So this is one example, and I will postpone the other example to the תרגול. Okay. So this is Watson's lemma. Now you can say I can put every Laplace integral in that form and implement Watson's lemma. How do I do that?
phi t שווה t.
Yeah, I will define, for every Laplace integral, I can define s is phi of t, right? I will change the variables and I will end up with integral of this form. Okay, and maybe playing with the limits of the integral, but I will get the same Watson's lemma. But in many cases, this is theoretically it is true. If you can do that, go do that. But it is, in many cases, very complicated, right? So it's better to work, in many cases, it is better to work with the original integral, this integral, and to implement, instead of implementing Watson's lemma, we can implement the Laplace technique for this integral. Okay. Now, what I have tried to convince you last time was that if I am going now directly to this integral, to the Laplace integral, there are three options. One of them is that the maximum of phi is at A, the maximum of phi is at B, and when I'm speaking about the maximum, I'm speaking about the global maximum in the interval between A and B, right? And the other is that the maximum is in between, in which case we can expand it. We have to find the maximum, and we have to expand phi around the maximum. Okay? Now I would like to present you the general formula. What is the general formula? The general formula, I mean, okay, when phi has a maximum, okay, so when phi has a maximum at A and at B, we have shown this last time, right? So forget about it. I assume now that the global maximum is somewhere in the interval between A and B. Inside the interval between A and B, okay? Now, let me assume that, okay, so I assume that the maximum is at C. So phi of C is the maximum, right? How should I write phi of T in general? Of say, of T minus C, right? Of T. Phi of T. So I will expand it. This is phi of C, and what we wrote last time in the when we did that, we said, okay, we have phi of C plus phi prime of C, which is a number, times T minus C, plus phi double prime of C over 2 times T minus C squared, blah blah blah. And then what was the observation? That because phi of C is the maximum, phi prime must be 0. So phi prime must be 0. This is the first non-vanishing contribution, and we continue expanding with this expansion. However, this should not be necessarily the case. Why? Because, yes?
What do you do if the function is from 0 to infinity? You don't necessarily have a maximum.
What does it mean? Okay, we will have
It's
an
not a
example.
complex space.
We will have an I mean, then the integral diverges.
But for here, for example, you have a maximum. Okay.
Okay? So this is what we did last time. And now I want to consider a more general case. More general case, I mean the case where maybe also the second derivative is 0. It may happen. Right? But so what will be the first contribution if the second derivative is 0?
The third derivative.
Because, okay, if it is a third derivative, then the point C cannot be a global maximum. Because then it implies that we have an inflection point, and yes, and it goes up either to the left or to the right of C. Okay, so it cannot be a global maximum. So, but it can be a fourth derivative, and so on and so forth. Okay, or a sixth derivative. Okay, so in the most general case, what I will have here instead of that. So, for example, if it is a fourth derivative, what? So, okay, so now we have a third derivative that we forget about, and we have the fourth derivative, which is phi bang 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 of C, divided by how much?
4.
Hmm?
4 factorial.
But yes,
20.
by 4 factorial times T minus C to the power of 4. This will be the term that we will have to consider. And in the most general case, what we will consider is phi of T is phi of C minus, or yes, phi, the pth derivative at c divided by p factorial t minus c to the power of p. Okay, plus and it will be negative. I mean, okay, to make it more, must be negative, because it goes down. Okay? Are you with me? It's a simple generalization of that. Instead of taking the second derivative, I'm taking a general expression. Okay? And then what I will get? If I plug it here, so what will be my my asymptotics to this integral? My asymptotics to this integral will be, first of all, I have f, I will take it at c, of course, as we did last time. Then I will take e to the x times phi of c, and now I have the integral from a to b, e to the minus x, phi absolute value, the pth derivative at c, divided by p factorial, times t minus c to the power of p, dt. Okay? And you know that, again, what I did in the last lecture, we extend the integration, we first shrink it to around c, and then we extend it to infinity. Right? So the integral will be from minus infinity to infinity. Okay? So again, if you put here p equals 2, you will get exactly what we did in the last lecture. But if you take p equals 4 or p equals 6, you will get the general contribution. By the way, just intuitively, the contribution for this will be larger as p grows larger or smaller.
What happened to f of t?
F is just f of c.
Why just f of c?
Because since the main contribution is coming from the immediate vicinity of c, you should take f to be just from this immediate vicinity. Next, we will consider cases where this is not exactly the case, but this is what we want now.
But
Okay?
couldn't we take a perturbation that f is as a vicinity that is not only c?
We will meet such an example. Wait for a moment. But for the moment, let's assume that this is what we are trying to do. So actually what we want, if you forget about everything except of this integral takes the form, integral from minus infinity to infinity of e to the minus alpha, let's say z to the p times dz, where I define z to be t minus c, and alpha is x, the pth derivative of c of phi at c absolute value divided by p factorial. Okay? And we know that if p is 2, this integral is e to the minus is square root of pi over alpha. Right? This is the formula we used. It's a Gaussian integral. This is the formula we used last time. Now, I will do the following. I will define, say, q as alpha times z to the p. First of all, because this integral is symmetric around 0, the 0 is a c, actually, right? Then I can write it as 2 times the integral from 0 to infinity, right? Because p is a even power. and this is equals to 2, and now I would like to write the integral from 0 to infinity of, if this is q is z, alpha z to the p, so z is q over alpha to the power of 1 over p. Right? And this implies that dz is q to the 1 over p minus 1 dq divided by alpha to the 1 over p. So what I have here is alpha to the 1 over p. You see? And here I have q to the 1 over p minus 1 times e to the minus q dq. Now what is that? This is again a gamma function. So I have 2 divided by alpha to the 1 over p times gamma of 1 over p. Okay? And when this has to be plugged instead of that. That's the integral. Where alpha is defined here. Right? So all in all, what we are going to get? The asymptotic of this integral, right, I, is asymptotic to what? To f of c times e to the x phi of c, and in general, when the first derivative that do not vanish is a piece derivative, we have what? We have 2 over alpha to the 1 over p, so here I have x to the 1 over p times the piece derivative at c absolute value to the power of 1 over p, and here I have p factorial to the power of 1 over p, and what else? This is the alpha, I have the 2, and gamma of 1 over p. Okay? This is a general formula, right? And if we plug p equals 2, just as a sanity check, right? What we have is f of c, e to the x phi of c, and now we have 2, and we have 2 factorial, which is 2 to the power of 1 over 2, so square root of 2, and we have gamma of 1/2, which is, I guess, square root of pi, right? Divided by x square root of x times phi, the second derivative absolute value at c, to the power of 1/2, and this is, let's see, so what is that? Gamma of square of 1/2 is square root of pi, right?
Yes.
What?
Yes, it's square root of 5.
Yes, exactly.
So we have square root of 2 pi. There is a factor of 2 that I don't like. Okay, let's make sure that what we wrote is the correct formula. Oh yeah, it's square root of 2 pi. Wait. Okay, the correct formula has a p here. Okay, now you have to, which takes out this 2, and this is the correct formula, p equals 2. Now, where this p came from? Sure. Here. If z is q to the power of 1 over p, right? Then dz is q to 1 over 10, and we have a p here. Yeah, I've taken the derivative of q to the power of 1 over p. It's q to the, but we have, you should multiply it by 1 over p. So we have p here. So there is a p here, and a p here, and a p here, and this is the correct formula. Fine. So this is a general formula when you have, note that, the factor here is x to the power of 1 over p. Right? So if p is 2, what is that? This is the estimation of the integrand at the point C. And this is the contribution from the integration around this point. And you see that if p is 2, then you have here 1 over square root of x. If p is 4, then you have here 1 over x to the 1/4, which is, as x goes to infinity, it's a much smaller reduction. You see? So you get much larger contribution when p is 4 than when p is 2. Why? Because when p is 2, you have something like, you are integrating over something like that, right? P is 4 means if the second derivative vanishes, it means that it's much more, see, something like that, right? It's much more, much less, much more flat here. When p goes to infinity, it's completely flat, right? So when you get much larger contribution, when the second derivative is also 0.
But then the approximation of saying that around the c is the same as the integral from infinity to infinity is invalid.
It's still true when x goes to infinity. It's still true. This is an asymptotic expansion. So as x goes to infinity, everything that is outside here is subdominant no matter what p is, as long as p is finite.
Even when p goes to infinity?
No, as long as p is finite, of course. If p goes to infinity, it implies that you are not integrating on, you have no maximum,
yes.
Right? So this is, but if p is, the larger p is, the smaller are the differences between the maximum point and its neighboring point, but still as x goes to infinity, the contribution is from the maximum. But the extra reduction due to the fact that you are integrating over only a finite area is becoming less important as p goes to infinity, right? And this is the explanation of the rainbow and all this phenomenon that has to do with the fact that the second derivative is vanishing and you have fourth derivative and so on. Okay, good. So this is essentially what we have to say about Laplace integrals. Now there are many examples, but again, I postpone the examples to the target. Instead of that, I would like to give another last comment on, okay, there is a whole subject that I'm not going to teach you, which is saddle points in complex plane, estimation of integrals by steepest descent method. If you want, you can read it in the book. I have no time to spend on that. And so the last example that I want to, as I told you, all this is good when f of t is at least behaving like a power when t goes to, it may diverge or go to 0, but as a power, right? Now let's speak about another example. So now I'm starting from an example. And my example is the integral from 0 to infinity, say, of e to the minus t minus xt dt, which is I. Right? You see? Now, what will happen if we will try to implement Watson's lemma? Or maybe I will. Maybe I have to go one step backward. No, that's fine. You see the problem? When f of t may be written that way, even if t is t to the minus 1/2, say, it diverges at 0, but I can still plug it here and I will get something great. E to the minus t cannot be written that way. It has an essential singularity at t equals 0.
But can you just say that f is 1 and x and just take x plus 1 instead of x?
What?
Like take like e to say y equal to x plus 1 and then it's e to the minus yt with ft equal to 1. And you can use the...
I didn't understand. Maybe you're right, but I don't understand what you're saying.
write it as a Lorentz series.
זה הרבה יותר פשוט מזה, פשוט לסמן את זה, לא משנה, נראה
מה?
פשוט להגיד שמינוס t מינוס xt שווה למינוס yt כש-y זה x פלוס 1
או,
אז אתה יכול פשוט להשתמש
אנחנו עושים משהו דומה. Okay. So, the point is that because of this horrible this is t, this is so. No. Sorry. I'm speaking nonsense. Right? This is the integral.
Okay.
So now it is going, e to the t have a very nice expansion. Okay, I was speaking nonsense. E to the minus 1 over t is doing horrible things at the vicinity of t equals 0. Right? So the actual how this actual function looks like, right? E to the minus xt is something like that. But now, because of the e to the minus 1 over t, you see, it will do something like that. There is always t which is small enough such that the contribution, such that the integrand is going to 0. And it happens in a way that you cannot write it in a power series, because e to the minus 1 over t has no power series. Okay? Do you agree? Good.
What happened in infinity?
Hmm?
In infinity, what happened?
In infinity, 1 over t is 0, so you don't care about that. So you just have e to the minus xt. Okay? Okay, in particular, let me just say that suppose I'm saying, okay, x is so large that I can neglect this. Just to be on, yes, what I will get?
boundary
Get
layer
one.
problem.
What?
Boundary layer problem.
No, I'm just neglecting it.
You get ft equal to 1.
I will get, what will be I?
E to the minus
What is the integral from 0 to infinity of e to the minus xt dt?
1 over x.
1 over x,
1 over x.
right? Okay? Just remember it. Now, I want to implement Laplace method to this integral, and as I said, I can't plug it into the f of t into Watson's lemma because it has no serious expansion. You see? What should I do? Okay? The trick is as follows. I will look for the point where you see that the maximum is here, it's not here. Right? So where is the maximum? Where is the maximum? I have to, I can write it as e to the minus f, say, when f is now xt, not f, g, where g is xt plus 1 over t. And I want the minimum of this function. Now, where is the minimum of this function? At what t?
1 over x squared.
So I'm taking derivative. So x minus 1 over t squared is 0. So this implies that t star, the point where I have a minimum for g, which is the maximum for my function, is 1 over square root of x. Right? For that reason, such cases are known as movable maxima. Movable maximum, because the larger x is, the smaller t star is, but it is always finite. Okay, so what is the trick? The trick is to do to change the variables. So I will define z as t over t star, meaning t over square root of x.
T over T star is T.
T over t star, which is square root of x t. So,
Yes. More.
right? So now, z, when t is around the maximum, z will be order 1. That's a goal of the game, right? So if z is square root of xt, then what is this integral? Right? First of all, the limits are still 0 and infinity. You see? And what I have inside? I have dt, which is dz over square root of x. And now I have e to the minus xt. But what is t? T is z over square root of x. So I have square root of x, z, right? And now I have minus 1 over t. 1 over t is square root of x over z.
But you just get the same problem.
No. Now what I have is 1 over square root of x times the integral from 0 to infinity of e to the minus square root of x times z plus 1 over z. And now you see the maximum is not at 0. The maximum is at z equals 1. Right? From here on, I continue the Laplace analysis. Right? This is, so phi is z plus 1 over z. Phi prime is 1 minus 1 over z squared, which implies that this will be 0 at z star equals 1. Right? This is phi. Phi of 1 is, sorry, phi of 1 is a minimum, right? And what, sorry, phi prime is 0 at z equals 1, and at z equals 1, this is 2, right? So phi of c is equals to 2. So what I have here is 1 over square root of x times the integral from 0 to infinity of e to the minus square root of x times, and now I will expand it. So I have 2, yes? And now what is phi double prime? Phi double prime is 1 over z cubed. 2 over z cubed, right? And I should plug here 1, right? So I have 2 minus 2 plus, sorry. So this is 1, right? But I need what I need to write here as phi double prime over of c over 2 times what?
Z minus 1.
times
Z minus
yes.
1.
Yes, okay, times z minus 1 squared, and I have the z, okay. So I have e to the minus 2 square root of x outside divided by square root of x, integral, and now instead of integrating from 0 to infinity, I can integrate from minus infinity to infinity, because I'm integrating around z equals 1, right? So I have minus infinity, infinity.
Wait, but it shouldn't be in it shouldn't be no in it doesn't matter. It's in
Right, so this is 2 and this is 2, they cancel out.
yeah.
Right? So what I have is just e to the minus, let's define z minus 1 as, I don't know, t again. So t squared dt. And this is square root of pi.
Square root of pi.
What?
Just square root of pi.
Square root of pi. So all in all, I have square root of pi times e to the minus 2 square root of x
But
divided
you have
by...
square root of x. But you have square root of x double this. It's minus square root of x.
Yes. Sorry, I have square root of x here.
So
Right?
it's
So it's square root of pi.
Okay.
So it's
No, square root of pi.
square root of pi divided by square root of x. So that I will have square root of pi, and here I have x to the 3/4. Right? That's asymptotics of this integral and not 1 over x. See? Yes, exactly. Exactly. Oh, I'm wasting my time on examples and I can. Okay, so I will save the next example to the targil again, and I will. Maybe it's not a good strategy, but I'm too close to the end of the. I mean, we have only one extra class, so okay. So I am. This is all what I wanted to tell you about asymptotics of integrals, and we will make more examples in the target. Okay. Now let's move to the next topic, which is, and I will, although I have only I have 40 minutes now. Okay. The next topic is the last topic of the course. And it's two-time perturbation theory, right? What does it mean? I will explain in a moment. Okay, good. Let's start with a problem that I guess you are familiar with. YD dot plus omega naught squared y equals 0. What are the solutions of this equation?
Harmonic oscillator.
It's an harmonic oscillator. Yes? So the solutions, you will not be surprised that the solutions are A e to the I omega naught t plus B e to the minus I omega naught t. You may say this is a cosine and sine, that's right. It's only another way to write the same thing, right? I'm doing that because in a moment you will see it's better to work with exponentials and assume that we are taking the real part. But, okay? Are we on the same page? Good. Now here is the problem. I want to solve the equation YD dot plus omega naught square y is equals to A times cosine of omega t. Okay? So you may think about it as what? What is that? What's the name of this problem in physics?
Damped harmonic.
Damped? No, this is not damped. This is forced.
Forced.
Forced. It's like having a force. you have a kid sitting on okay, you have a kid sitting on the swing, and this is you. You apply force, right? And although your force, the force you are applying is not exactly periodic, you can just Fourier it into harmonic. So you have many A's of this, right? And we are looking at one of them. Okay? Good. So you understand the scenario. Good. Now, and again, what I would like to do is to write this as e to the I omega t, assuming that we are taking the real part. Fine. How one should solve such an equation? There are many ways, but the canonical way is to look at it and say, okay, what we have here is a inhomogeneous linear equation. And the answer for an inhomogeneous linear equation, as you know, is a linear combination of the solutions of the homogeneous linear equation plus a spatial solution. And how do we find the spatial solution? We are doing variation of coefficients, right? Variation, I don't know. Variation of parameters, yes. And what is the formula for the variation of parameters? What?
With the Vronsky.
Okay. So first of all, what are the solutions? These are the homogeneous solutions, right? E to the I omega t, e to the minus omega t. What is the Vronsky?
1.
Not exactly. We have e to the I omega t, e to the minus I omega t, I omega. Sorry, this is omega naught, right? I omega naught e to the I omega naught t, I omega naught minus I omega naught e to the minus I omega naught t, and we have to take the absolute value of the determinant of this garbage. So the exponents are killing each other, and what we have is 2 omega naught. Again, the absolute value, we have another I here that cancels out, right? So this is the Vronsky. Now the spatial solution will be y is equal to, if I remember it correctly, minus y1, the integral of y2. y1 and y2 are this and that. This is y1, say, and this is y2, right? Minus y1 integral over y2 times f. F is this is f, right? Divided by the Vronsky plus y2 integral. The integral is up to t, no matter what is this is spatial solution. And here we have y2 and y1f divided by the Vronsky again, dt prime. Okay, now let's write it. What it will be? It will be minus e to the I omega naught t divided by, so the Vronsky is 2 omega naught, I can take it outside. I can, from the f, I can take the a outside. Okay, and what I have inside here is the integral up to t of e to the, okay, so f is I omega t, and I have omega minus omega naught t. You see why? The omega is coming from the f, and the omega naught is a y2. Okay?
T prime.
What?
T prime. T prime. Because
T
they are
prime,
integrating
sure.
it.
T prime, dt prime. And this is, and there is a minus here, I guess. And then we have plus a e to the minus I omega naught t divided by 2 omega naught, and the integral for up to t of e to the I. Here we have omega plus omega naught, right? T prime dt prime. Do you agree with me? So what are these integrals? We know how to do them. So what we will get is a e to the I omega naught t divided by 2 omega naught times omega minus omega naught. You see? Maybe I have an I here. So I can put the I here and kill the minus. And no, and then I have this. I have e to the I omega minus omega naught t, right? So the minus will go out and I will have only e to the I omega t. And from here I will get plus, actually the same thing up to, what's the difference between the two?
Just in the denominator.
Yes. So I will have I a e to the I omega t again, because again the omega naught cancels out, divided by 2 omega naught times omega plus omega naught. That's it. Something like that. Okay? Now, what is the meaning of this solution? Of course, we should take the real part. Okay? But you see what do I want to say? For some reason I couldn't print my notes for this part of the lecture. So I have to look here. Okay, so if I will take now the real part of that, right? So I have I e to the I, this will give me a sign. So up to maybe a factor of 2 or something, I will get a sine of
Minus
omega t divided by 2 omega naught. Maybe the 2 is going away also because what?
It's
No.
minus in
No.
somewhere.
So I have a, or let's write it that way, a over 2 omega naught sine of omega t divided by omega minus omega naught. Right. Plus sine omega t divided by omega plus omega.
It should be minus all that because I times I is minus 1.
Whatever. Who cares about the phase? Right? So the point is that what we will get is something, okay, that is without the factors here, we will get something that is just doing the spatial solution is just something that is doing oscillations at the frequency of the force. Okay? Because you know that the force is taking over the frequency in the harmonic oscillators. However, we have this factor. And this factor implies that when the frequency of the force is equal or become close or minus or whatever, okay? The frequency of the oscillator, we will get something that is growing linearly in time, right? No. Okay. There is a mistake here, sorry. There is a mistake here. One second. Why can't I see the... Anyhow, it's not so important, but this is omega minus omega naught times t, sorry, and this is omega plus omega naught times t. Now, why I have this omega?
Because when omega close into omega naught, it's like a single value.
Yes, but how did you get this argument of the sign?
Yeah,
Wait, what?
I don't see that. But anyhow, this is the correct solution. It's not so, I mean, what is important is that, for example, if you look at such a term, right, and you analyze what's happened when omega is approaching omega naught, what you're going to get?
Omega minus omega naught. Sin is
Sine.
one.
You have
One.
when omega is approaching omega naught, you have omega minus omega naught t divided by omega minus omega naught, and this cancels out, right? And you get t. So this is what, this is exactly what this term does when omega is approaching minus omega. So what you will get when omega is close to omega naught, right, is a resonance. It's a known phenomenon. There are many ways to solve it, and I managed to do it in the wrong way. But the resonance, you have the amplitude of the oscillations is growing, right? And you have something that is doing something with that, right? With a frequency that belongs to the other term, but it is growing and growing, right? Until when? When it stops growing. So for every omega minus omega naught, when t is larger than 1 over omega minus omega naught, say, then it stops growing. Right, so we have something that is growing linearly, amplitude that is growing linearly, and at some point it stops growing. But when omega is equal to omega naught, it is growing linearly forever. That's the known phenomenon of resonance, very important in all parts of physics, but you know, every time you hit the resonance of a system, it starts getting crazy, so on and so forth. Okay? So, except of the weird mistake that I have here with the argument of the sign, but this is the correct thing. You can plug it into the equation and see that this is actually the spatial solution.
So if we go back to the example of the swing.
Wait, maybe I didn't. Usually I'm doing it in a different way. I have no time to waste on that because it's not important for what we are doing from now on. You just have to remember that there is this, what they call secular solution. Why it is secular, I don't know, but it's called secular solution. The secular solution, when omega is equal to omega naught, you have something that diverges. Okay? Are you with me? Fine. So, maybe I should have to skip all this example, but now here is the important point. Now this was, you know, all this is in the realm of exact solutions. We didn't do any tricky thing. Now let's speak about the topic of this course, namely perturbation theory. So what I would like to speak about is an equation of the form. Let me just fix the notation. Yes. So I want the equation y d dot plus y. If I have just this equals 0, then it will be harmonic oscillator. And what's the difference between this and the former harmonic oscillator?
Omega is equal to 1.
What's the difference between this and that?
Omega is equal to
Omega naught is 1. Okay, so from now on, omega naught is taken to be 1. We can always do that by changing our time unit. Okay, omega naught is 1. However, I would like now to add epsilon y cubed equals 0, where y of 0 is 1 and y dot of 0 is 0. This is the equation I want to solve. Now, have we encountered such a problem in the past? In the past, I mean in the past of this course? Yes. What is that? This is a harmonic oscillator with quartic term. You remember that we did something like minus x squared over 4 plus x to the 4 over, yes? So this is actually the first correction for every harmonic oscillator, right? You have an harmonic oscillator. The force is towards the fixed point, right? Okay. You have harmonic oscillator, and you know that f is minus kx, right? So this is, and x d dot is f, so it's okay up to it's minus x. So x d dot plus x is 0, right? This is harmonic oscillator. But this is the behavior. This is true only in materials that are perfectly elastic.
Or small deformations.
Oh yeah,
So
or
that's
it's the limit of small
correction.
deformations.
Yes.
Every finite deformation will involve more terms here, but the terms should be restoring force, right? Because they want, so you can't write it something like minus x squared, because this is taking you to the wrong side, right? It should be x cubed minus x fifth with whatever
You
coefficient.
also can't have x squared because you're in the minimum.
What?
You're in
Yes.
the minimum, so you can't have x
So yes. So the first correction is that, which is here, right? So this is actually true in every spring, right? You can see that if you take the spring and stretch it and then leave it with the mass, it will have some it will oscillate with a certain periodicity. If you take it more, if you stretch it a little bit more, the periodicity will change a little bit. And this change is not it is only because you have such an anharmonic term. So this is just anharmonic oscillator, and it's actually everywhere, right? There is no harmonic oscillator in the world, right? Every harmonic motion have some sort of small correction with anharmonicity. Anharmonicity, whatever. Anharmonic, some anharmonic term. Okay. So now, what all physicists are doing all the time, they just kill this term and solve the problem and they are happy. But this term is actually here in every practical problem. Okay. So what do we want to do? What I taught you until in the first lecture of this semester, I guess I gave you, I waved my hand and told you that you must have perturbative expansion in order to understand physics, because there is no perfect physical situation. Yes?
Why isn't it a problem in global analysis?
What?
Why isn't it?
Of course it's a problem. We are doing global analysis for a while.
So why can't you simply use global analysis to solve this problem?
I will show you. Okay? So the simplest way to approach this problem is to assume, okay, let's assume that epsilon is small. That's a global analysis technique, right?
Yes.
Solve the problem in series of, okay, so here I'm following your advice, and I'm writing y of t as y naught of t plus epsilon y1 of t plus epsilon squared y2 of t, and I will plug it here and let's see what will happen.
Yes, of course.
Okay, good. Very nice. So we are following your advice. Okay, yeah. Which will turn out to be an Achitophel advice. Okay. So my first, I'm collecting terms to the power of epsilon to the 0. So what I have is y naught d dot plus y naught equals 0. Right?
This is a simple harmonic oscillator.
This is simple harmonic oscillator. And the answer will be, and of course, if you remember, I have to plug the initial conditions only at y in the first term. All the other terms, the initial conditions are 0, 0. But in the y naught, I will do that. And if I want, so the solution is a cosine t plus b sine t. And now, what it will give me if I'm taking, if I'm plugging the initial conditions?
It will give you
On the 0 solution.
It will give you that b equals to 0.
Yes, and a?
Also.
And a equals to 1.
Good. So the answer is y naught is cosine t. Very good. Okay, now epsilon to the 1. So what is the equation now? I'm plugging this into that and collecting term up to order epsilon. What's the answer?
What the answer is?
Again, I'm collecting only terms that are order epsilon.
So we have y.
So you have
y1
epsilon y1 dot.
No, I put the epsilon outside, right?
Yeah.
y1 double y
y1 double dot, right?
plus y1
Plus y1
plus
equals
y0
plus
y0 to the 3.
y0 cubed equals 0. So what I have gotten is y1 double dot plus y1 is equals to minus cosine cubed of t.
That's
Not
not very nice.
very nice, but not impossible.
Okay, but it will keep getting worse.
Okay, it's simply mathematics. It's
Okay,
not something
who
that's-
remember? Okay, and now you only have to remember that cosinus cubed of t is 1/4 cosine 3t minus 3/4, the minus is from here, yes? Cosine t. Yes. And now you see what deep problem we are. Because we have harmonic oscillator, which is forced, and one of the forces is at resonance. And it will cause the solution to diverge. Okay, that's a problem. That's a problem. That's why you cannot use the naive global analysis approach in such a case.
Because of the resonance?
Yes, because the problem, you see, the resonance is self-generated. It's not that I impose on the system something which is at resonance. I only put the y cubed, which is completely fair term. And because the y0 is oscillating, the y cubed contains something that is at resonance with the y0, with the harmonic oscillator. And that, for that reason, I will get to the first power, I will get something that diverges in t, and I'm in big trouble. Right? So the idea of two-time perturbation theory is to devise a trick that will allow us to get rid of this problem. But for the moment, just to make sure that you understand what the problem is. Okay? You are with me. Good. Now, so what's the trick? Okay, just maybe I will just try to present it technically, completely technically now, and next lecture I will elaborate on that. So the trick is, I'm saying as follows: from now on, from this moment on, I will assume that just to make sure that I'm not missing something. You may ask, maybe this is actually the case. Maybe I'm starting from y naught equals 1, y dot is 0, and and I will diverge. As time goes to infinity, I will go to infinity. Is it possible that this is indeed the case?
I think not, but I'm not sure why.
Okay, very simple. This is actually the equation, if you want to write it, x d dot is minus dou v dou x, where v is x squared over 2 plus epsilon x to the 4 over 4. Do you agree with me? Right? This equation and this equation are the same. Now, when I show you it that way, you understand that this is a problem with the potential, and it conserves energy. Right? So x dot squared plus x squared over 2 plus epsilon x squared over x to the 4 over 4 is a conserved quantity. So it cannot be, and I started at x dot equals 0, x equals 1. So the energy, right, this is the total energy. The energy at time 0 is 1/2 plus epsilon 1/4, and that's it. That's energy. There is no way that the particle will diverge to infinity. Okay? Good. So, what should I do? Here is a trick. Here I will define a new variable. The new variable will be tau, and tau will be epsilon times t. Right? Note that what we found is that we have the solution, the first order solution is diverging. Right? But when it will become severe problem, right, it is diverging linearly, and the problem will become severe when t is going like 1 over epsilon. So I'm defining a new time variable, and from now on, we assume that y is not a function of t, but it's a function of t and tau. I will treat them as completely different variables.
You can do this.
Yes, of course. Here, you see, right? I will take t and tau, so I'm writing y is, just to, instead of writing it like that, right? I will write it as y equals to z naught of t and tau plus epsilon z1 of t and tau plus epsilon squared z2 of t and tau. So this is like that, exactly like that, but instead of writing functions of t, I'm writing functions of t and tau. Okay?
How will you take the derivative?
Oh, very good, very good. So everywhere where here I have ddt, so ddt is now dou dt plus dou d tau dt. But what is d tau dt?
Epsilon.
Epsilon. Very good. So what will be d squared dt squared? Or maybe I will write, what will be y dot?
It will be z0
dz0 dt plus epsilon dz0 d tau
tau
plus epsilon dz1 dt plus epsilon squared dz1 d tau, and so on and so forth. What will be y d dot? I should take this operator and work on this again. What it will give me?
Second derivative with respect of time. Plus epsilon divided.
Let's keep all terms that are the order epsilon. Right? What are the contributions?
Dou z naught z dot tau.
Epsilon. Okay.
This with t and tau.
Okay, I can take the second derivative of epsilon dot tau can work on that, and ddt can work on that. In both, so I will get 2
2.
times second derivative of z naught with respect to t and tau. This is one contribution that is order epsilon. What other contribution of order epsilon I have?
The tau dot t.
This working on that.
So
Right? So I'll have plus
dot z1
d2z1 d tau squared.
t.
D t squared. Yes. Plus things that are order epsilon squared and so on. Okay? You see what I'm doing?
Yes, but you have also epsilon tau.
Again, I'm using the same trickery that I used before, but now with 2 times, with t and tau. Keeping in mind, in the back of my mind, for the moment I will deny it, that we have this relationship. Okay? Good. Now, and now by having done that, I'm continue in the general approach of global analysis.
Yes.
I'm following your advice, but now it is twisted with that. So what will be the equation to the 0th power in epsilon?
d0 d squared z0 to dt squared plus z0
Plus
z0
equals
0.
right? Forget for the moment about the initial conditions. It will be another headache. But for the moment, just okay. What the solution is?
It should be a second derivative and
Of course.
Sine
Cosine
cosine.
is fine.
Sine cosine.
What?
Harmonic oscillator.
Harmonic oscillator.
Harmonic oscillator.
Sine plus.
Okay, so
But
Z naught
the constant
is
should be dependent on tau.
very good. Thank you very much. You're a genius. Okay? A of tau e to the I t plus conjugate A of tau e to the minus it, if I want the zero to be right? So I have an undefined dependency of A on tau that I can take whatever I like because I have this equation. Right? This equation is only for theta. Ouch.
But shouldn't you have the dependency on how we call this? The dependency of the initial conditions.
Wait, I didn't plug the initial condition in yet. Okay? Now, what I have to the first power of epsilon? Okay, I'm in.
You have
Should I continue for 15 minutes or should I continue after the break?
Take a
You want?
continue.
You give me 15 minutes now. Are you all agree with him? Yes. Okay. So what we have to the first power of epsilon?
You have two d.
What?
You have a two.
I have
This two.
this.
This.
This is going into the y dot. So I have d2z1 dt squared plus
Two.
plus
Plus
z1 equals to what? So first of all I have minus 2 d2z naught dt d tau. You see? And I have this y cubed. So I have here minus z naught cubed. Okay? Good. This should be equal to 0. No, this is equal to 0. Okay? So now what I have? I have d2z1 dt squared plus z1 equals to, okay. So first of all, z naught cubed, I have minus of a cubed e to the 3it plus a squared a star e to the it plus a star squared e to the it e to the minus it plus a star cubed e to the minus 3it. All this is z naught cubed.
We assume that A star and A and A star are conjugated variables.
That's why I'm denoting them by a and a star. Right? And now I have minus 2, and I have to take now the derivative with respect to t and tau. So we have, in the first term, we have minus 2i a dot e to the it minus 2i, okay, it's not, it's the a dot tau, just to, right? And here we have do a star dot tau e to the minus it.
It's plus.
Plus.
E to the,
It's plus.
It's plus.
No, not in
it's,
this.
this is plus.
Yeah.
Yes, good. Okay, fine. So, do you agree? Now,
Archimedes coefficients in the
which
Three.
coefficient?
Three. In the first.
Ah, sure,
Yes.
sure. Thank you very much. You saved my life. 3. Of course. 1, 3, 3, 1. Yes. Good. Now, here is the point. This is a horrible equation.
Yes.
You look at it and you say, oh no, why do we have to deal with such a monster? And the point is that we don't have, at least to this order in perturbation theory, we don't have to deal with a monster. We only have to take care of one very simple thing. And that is, you remember what causes us the troubles to begin with. Yes? The problem was that we got here we have an homogeneous equation for Z1, and we got a driving force that causes a resonance, that causes the thing to diverge. All I want to do is to fix A by the condition that there is no resonance.
Oh,
This is all I want to do.
this is smart.
That's great. So which term should I kill in order to have no resonance? Who are the dangerous guys?
Yes. A2, A2.
This?
Yes.
This, and this should go away. You see?
Yeah.
That's the only requirement. The only real requirement is that these guys will go to hell. And this, at least for the first order in perturbation theory, will give me something which is, so actually I'm not even doing the first order. I'm just doing the first order just to the level that allow me to determine how to avoid the resonances in the solution.
You can solve those. You can solve an equation for those.
Of course you can solve the damn monster, but this is not what we are going to do. All we are going to do...
I mean, now you need to somehow find A according to the...
Exactly, because now I have an equation. For example, think about this and that. Right? This equation just tells me that 3 A absolute value squared, which is AA star times A,
E to the I.
plus 2I do A do tau must be equal to 0. Say it another way, do A do tau must be equal to minus 3/2 A absolute value squared A, and I have to divide it by I, so I'll write it at plus 3I. Now, this was good for these two terms. What about these two terms? They are the complex conjugate of these guys. So it will be, once I will satisfy that, I will satisfy that also. So this is the only equation I have to satisfy in order to avoid the explosion of the first order term. Okay? Now, how to continue? I will take A to be of the form R of t e to the I theta of t. And then what is of tau. So what's written here is do R do tau plus I R of tau times do theta do tau. All this is multiplied by the exponent,
Okay,
right?
yes,
But it will equals 3I divided by 2. This is R squared
of
tau, and this A is R times e to the I theta. The e to the I theta will cancel, and the R squared, so I will have here R cubed. Good. Now I have an equation that has R and theta are both real functions. And for that reason, this equation should be satisfied. There are two equations here. Right? The real part and the imaginary part should cancel separately. So R is constant. So R is simply R, some constant. R is constant. And what about and dot theta, dot tau is 3/2 of
R squared.
R squared.
You just get
So theta of tau
is linear.
is 3/2 R squared tau plus constant, let's call it phi. Good.
Now you have the initial condition.
Okay, so now I have actually this. Now I'm going back to the first order, to the zeroth order. I'm not doing anything above the zeroth order. All I use the first order for is to find what are the conditions to solve for A in order that in order to make sure that the solution will not explode. Right? I didn't really solve the first order. All I extracted from the first order are the conditions for the zeroth order not to explode in the next order in perturbation theory.
But the zeroth order didn't explode even.
No, because you have the A of tau.
Okay.
Okay? So now I can write the solution of the zeroth order. And the solution of the zeroth order is Z0 is A, and A is R, and I have e to the something, so it will be R e to the what?
The I of theta.
To the I times 3/2 R squared tau
Plus phi.
plus
Phi.
plus
Plus phi.
no plus t plus phi, right? Because I have this t
Yeah.
plus complex conjugate,
Which
Okay.
is the same thing. Just
which
in
is
the
cosine. So Z0 at the end is some okay. And of course I can. The constant is not part of the story because I can multiply it by constant. So this R is meaningless, right? So what I have is Z0 is some constant, let's call it C, times cosine of 3/2 R squared tau plus T plus phi.
If you change the R to C, you need to change the R to C even in the inside because now
Yes.
you have
R is simply.
No, here you have an arbitrary constant that multiply all that.
but now you have more.
You have three constants.
Yes.
What?
You have
Now you have
second
three
order.
constants and two equations.
You have second order differential
No,
equation.
I am calling. I have a constant here. Let's call it C1.
Okay.
Right now, I will define C1R as C2.
Okay.
This will be C2.
But
Okay.
you still have. How do you define C, R, and phi?
Okay. Now I have to go back to the initial conditions.
Okay.
Okay. But before going back to the initial conditions, I have to remind myself that tau is actually epsilon t. Right? So what I will write here is some C2 times cosine of 3/2 R squared
Epsilon t
times epsilon t
plus t
plus t
plus.
plus phi. Right?
Now when t equals to 0.
No, sorry. Okay. T plus phi plus 3/2. Okay, everything is good except that. No, I want to do it with the R.
Okay.
Okay.
Yeah.
So here I have now 2R,
Okay.
2R, and this is 2R. Okay, and all the rest are exactly the same. And I just want to write it in a single expression. So I have here 3/2 r epsilon tau t, right, plus t
R squared.
r squared plus t plus phi. Okay? And now I have to plug the initial conditions.
Yes.
So now I've exhausted also the 15 minutes. Okay, this is the main story. Okay? So I will spend. Okay, let's take now half an hour break. I will spend the first 15 minutes after the break on just giving you the final answer. I guess it will take less than 15 minutes. Then we have 1 hour of targil, and then next week. So I still owe you half an hour of targil. I guess that next week will be all targil, all the 4 hours.
Okay.
So okay, let's take a break here. Good. So we started from this equation. We developed the two-time perturbation theory that we did. This is an example, and next week we will have more examples. And we ended up with that. Right? This is, okay, we ended up with that, and then we plugged the original definition of tau. Right? Note that we didn't really, we didn't really implement the first order perturbative expansion. We used it only in order to make sure that the wrong, we only make sure that the solution do not explode, right? And we end up with it. Now we have to plug the initial conditions, but we are doing that to zeroth order in epsilon, right? So because we are plugging the initial condition in the y naught, if you remember it, right? So to zeroth order in epsilon, we are okay. So this is the solution, and now what we want? We want y of 0 to be 0, so to be 1. So 2r times cosine phi has to be 1.
Phi will be 0.
Wait. That we have two constants, r and phi. 2r cosine phi is 1, and y dot is 2r times sine phi times times 1 plus 3/2 r squared epsilon. All this should be 0. Okay? So actually we do not have to take this into account because this is first order in epsilon, but even if you take it into account, you can see that we can easily satisfy this initial condition by assuming that phi is 0 and r is 1/2. You see? And this is the grand finale of the whole thing. Extremely interesting. Which is that y turns out to be, y naught actually, the first, or z naught, the first order perturbation, okay. In a moment we will understand what order is it in what, right? Is actually 2r, but r is 1/2, so it's 1, times cosine of phi 0, so we have t, times 1, this is that t, plus 3/2 of r squared times epsilon, but r is 1/2. So 3/2 r squared is 3/8. So what we have here is 3/8 epsilon times t. So, bottom line, what we have obtained here is that the contribution, okay, so first, what's happened here? Or let's write it that way. First, same thing. what we obtained is correction, but not in epsilon, but in epsilon t. Right? Because we have seen that if we do a naive perturbation theory, this term will generate something that will grow linearly, and at time 1 over epsilon, it will be a big number. Right? So epsilon t is a time scale on which we have changes. Right? So we have a solution, we have something that is 0th order in epsilon, but remember, tau was epsilon t. It's first order in tau, say. Right? It's 0th order in epsilon, first order in tau. If we will do higher and higher expansions, which will be real headache, right? We will find contributions that are actually proportional to epsilon. And what is important to understand is that what is the meaning of set? So what was the effect of an anharmonicity? This is an anharmonicity, right? That's an anharmonic oscillator. What was the actual effect of anharmonicity?
The amplitude is dependent on frequency.
No, the amplitude is, we have a cosine, right?
No, but the amplitude too are
It's
depends on the frequency.
Yeah.
I told them in the course of numerical analysis that once I have talked to a mathematics professor who immigrated from Russia. So he told me that while in Russia he once talked to a general of the artillery, and the general asked him, "What are you doing?" And he said, "Well, I am a mathematician. I'm working with all kinds of functions." So the general asked him, "Do you know what a sine function is?" So he said, "Yes, of course. Sine function is something that oscillates between -1 and 1. So the general of the artillery said, "What? No, -1? No, sorry. The general of the artillery said, "Yes, in the artillery we also doing a lot of mathematical analysis. Do you know what is a sine function?" And he answers that, and the general said, "Sine between -1 and 1. When we need it in Afghanistan, it may become 5." So why did I say that? Yeah, because the cosine is still between -1 and 1. But what's happened, you can write it as cosine of omega t, and now omega is not 1, right?
Yes.
Omega is 1 plus 3/8 times epsilon.
So the change was to the frequency.
Yes, yes. The effect of the anharmonicity, it is still going from -1 to 1. So of course the anharmonicity, I mean, it must go from -1. No. Yes.
This is because you choose the
It must go from -1 to 1 because of the conservation of energy, but it changes the. Where are my pens? Did I take them with me to the?
You need marker?
Okay, let me. Maybe it will be. Why did I took it? Okay, 1 second. I will bring them from my office.
I have. We have plenty. Yeah.
You have plenty.
We took it from the department.
Also,
It's fine.
fine. Okay, if you took it from the department.
enough.
Okay, yes. טור מכפל, אוקיי. שתיים לזה. טוב. So this was, as I said, this was a presentation of the essence of the two-time perturbation theory, and then next week we will do 2-3 other examples in order to make it. I mean, every example takes time, but the basic trick is here. You see, the basic trick is to filter out the terms that are going to explode. And
So
yes.
in the third order, we also didn't get, won't get that amplitude changes with epsilon.
sorry?
it's only
if we will
zero
calculate
solutions.
the first order,
Yes.
then okay, after choosing the A's, all these guys are going to help,
Yes.
right? And you end up for Z1 with a inhomogeneous equation, right? You have this, and you have these two terms that are cosine of 3t, essentially, right? You know what A is now, and you have here cosine of 3t. What was A? What was A?
It was R
E to I.
R e to the I that
I. Yeah, but what was theta?
3/2 R squared times tau plus
Tau.
Plus
Okay.
V.
What?
plus V, but
Plus phi. Well,
Yes.
okay, let's take phi to 0. So if I will plug it here, right, then I will get something that is pretty much right, I will get cosine of, where is epsilon, by the way?
in tau. Inside
In tau, that's epsilon t, right? So I will get something that is, I will get some perturbation with a frequency. It will not be cosine 3t, it will be cosine, but it will be cosine 3, it will be very, very much close to z.
Yeah.
So you will get something like z1 d dot plus z1 equals to maybe minus whatever cosine, or r maybe cosine of 3t plus 3/2 r squared epsilon t. Right? And this is solvable now, because the answer will not explode. Right? Because the frequency, this frequency is not 1. Right? So you can now solve for Z1. Right? Now, again, this is a function of t. Okay? So you will solve for Z1 and you will get coefficients that are function of tau. Functions of tau, and you will determine these coefficients with a second order expansion. But you see that this will give you something that goes like epsilon times some, something that will look like that. Right? So this will give a contribution not only to the phase, but also to the amplitude. You will get something like y is this, right? Y naught plus epsilon times cosine of something like 3t or something like that, divided by 2, right? Divided by 3 minus 1, so 2 or something. Yes, this frequency divided minus 1, minus the
yeah.
yes. So you will get something like
Like omega minus
this
omega
is like the omega minus omega naught,
Yes. Okay.
right? And so on and so forth.
Basically, every time you do two-time perturbation, you should expect some dependency between the amplitude and the frequency, right? I mean, usually, even when we look at the tuteled pendulum,
Yeah.
if I'm look only on small angles, it's all linear, and there is no dependency
Yes.
between them. But if we look on large angle, there will be dependency.
Yeah, but this is exactly that. I mean,
Yeah,
the
I'm
first
asking-
correction, if you have a pendulum, then you are saying like theta d dot, right, is minus theta again. Or let's take all
Yes,
constants. So theta d dot is minus sine theta. That's a pendulum, right? So to first so theta d dot is minus theta plus, and now you have theta cube divided by 6. So this
Yes.
is exactly what we did.
So I'm asking, but
So the 1/6 is our 1/6 is
Yeah.
our epsilon.
no, but I'm
Super.
asking if is this occurring characterization of the two-time perturbation. Every time I do two-time perturbation, I'm expecting a relationship between the amplitude and the frequency, or not?
To give a general statement here, I'm not sure. I'm not experienced enough with that, right? But right. You know that, okay, and you can also add the driving force here, right, that is time dependent, which is not, okay, now, what we did is exactly that, now, right?
Yes.
And, but of course, you can also add to the pendulum time dependent, like something like, something like that, right? And then you have, you know that if you choose the frequency here in the right way, you can stabilize the upside down pendulum. See what I'm saying?
No.
No. If you have a pendulum, the pendulum have this, this is a stable fixed point, and this is an unstable fixed point, right? If you are here and you move a little bit, you are going away from this point, right? But if you play with, you are moving this up and down in the correct frequency, then it stabilizes this point.
Okay.
This is called Kapitsa pendulum. Kapitsa was the, I think that he was the advisor of Lev Landau. Piotr Kapitsa. He brought, I think, he brought some part of modern physics to Russia. I don't know which one, but exactly, I don't know. I mean, he was a famous physicist. I guess he got the Nobel Prize.
Yeah.
Yeah?
I think so.
But for what? Not for the Kapitsa pendulum.
No.
Something else. I don't know. I don't remember. He also, by the way, a very interesting point, when World War, I mean, when the Germans invaded Russia in 1941, right? Before that, they have Ribbentrop-Molotov agreement, and they were best friends. And actually, all the communists in the West said we shouldn't enter the war because the war was against Germany, and Germany was an ally of Russia. Then one day, Germany invaded Russia, and of course their policy have changed by 180 degrees at once, and from that point on they wanted United States to enter the war as fast as they can. So part of that, they have established what they called an anti-fascist Jewish committee, in which they put famous Jews that were leading figures in Russia, mainly cultural figures, not political figures, but famous actors and writers, people like that, and their role was to call to the Jews in the United States to push the government to enter the war. And for some obscure reason, Piotr Kapitsa was also a member of this committee, despite not being Jewish. But it helped him because when after the war, a few years after the war, Stalin decided that he wanted to get rid of this committee, so they were executed, all of them except of Kapitsa. So he was.
Why?
you can't answer such questions about the Stalinist regime because they essentially the probability to kill a person was independent of any factor, right? I mean,
They kill everyone anytime, any moment.
yeah, they were not. There was no rule. I mean, nobody knows
There's no
who will be next, and nobody knows what to do in order to avoid being arrested and get shot. I mean, that was very interesting. So until now, people are trying to rationalize, right? What Stalin was thinking when he decided to shoot all the guys from Poland, then to shoot all his best advisors, then to shoot all the peasants that have more than X money, and so on and so forth. So it's a good question. Nobody knows.
Pizza got a Nobel Prize for super liquid
Okay.
liquid hydrogen.
Liquid
Hydrogen.
hydrogen.
Yeah.
So it's not, no.
I mean, he
Kremlin
proved it
honest.
theoretically.
Okay. Whatever. Fine. Anyhow. By the way, here is something that I discovered yesterday. Why matrix is the name of the matrix?
Because of the movie. It was a joke.
Right?
I saw your post tomorrow.
That's so it isn't fair.
That's all I did. Was to go down.
So the meaning of a matrix in Latin is a womb. Like mother,
Womb.
it's a rechem. Yes. And it was James Joseph Sylvester, one of the fathers of linear algebra, who decided that the same way womb produces kids, the matrix produces solutions to linear equations. So that's why it's called the matrix. Very interesting.
I'm not sure this is exactly how kids come to the world.
Okay. Yeah, I mean you can, but
He doesn't really know.
you should know that once in one of his lectures in some university, he was British, but he spent some of his career in America, and he was teaching in Philadelphia University or some university in Pennsylvania, I guess. And in one of his lectures, he got angry about a student, and they had a fight, and he hit him so badly he thought he killed the student. So he escaped to New York, and then he realized that the student stayed alive. So he came back, but then he left the university because he felt that the university didn't punish the student enough. היו זמנים שללמד באוניברסיטה זה היה משעשע. Okay. So let's go back to the integration thing. First of all, okay, we have I, which is the integral from A to B of f of t e to the x phi of t dt. Right? This is what we want to estimate at the limit of x goes to infinity. Now, we did discover actually 4 formulas. So let's write first of all the formulas. What's happened when the maximum, so if the absolute maximum is at A, then we have to take minus f of A e to the x phi of A divided by phi prime of A times x. And what's important, okay, I usually took this with absolute value. So now this is without the absolute value. Okay?
Should
Now-
we double try?
No. This is because it's a maximum at x. If you remember,
It's not a global maximum.
it's a global maximum in the regime between A and B, but it shouldn't be that shouldn't be a maximum of the function.
It's not a
Ah.
local
It's
maximum.
local maximum.
It's not a local maximum. Fine.
Okay.
Now, what's happened when the maximum is at B, and then we have only x here, and not square root of x, if you remember, because we integrated. Okay? These are the formulas. So it's the same thing except that we have no minus. The minus has to do with the direction of the, right? So we have f of b, e to the x, phi of b, divided by phi prime of b times x. Okay? Now, what's happened when? So we have this, these are two formulas. Now we may have a max at some point C between A and B, and then, and we have first derivative is not zero, second derivative, sorry, is not zero, first derivative is zero, because it's a maximum, the second derivative is not zero, and then we have square root of 2 pi times f of C, e to the x phi of C, divided by square root of x times what it was times phi double prime. And I should put a minus here because the phi double prime is by definition negative. Right, this was the third formula. And the general formula, if the maximum is at C between A and B, but phi of P is not zero, when P is the first derivative that is not going to zero, then what we obtain is 2, of course, again, f of C, e to the x phi of C, this is always there. Now we have gamma of 1 over P, and we have P here, and we have P factorial. P factorial to the 1 over P, and down here we have minus x times the P's derivative at C to the power of 1 over P. Right? Yeah.
And also P in the
What?
we wrote okay.
Yeah. Okay, so these are the four formulas that we can write, number A, B, C, and D.
Because of that.
After not finding it.
What?
Now we remember the P after not finding it before.
Yes.
Yes. Okay. Now let's start playing with exercises, and to begin with, it will be trivial because we will just plug in the formulas, but then we will start to see something that is not exactly in parallel with the formulas. So first of all, I want the integral from 0 to pi over 2 of e to the minus x times tangents t dt. Right? Which formula we are going to apply?
That's for B. B
Hmm?
maximum.
Ah,
What the tangents is doing between 0 and pi over 2?
Just growing.
yes. But because of
It's 0 at
minus
0 and goes to
zero
infinity
is
at power over 2.
Zero.
So clearly where the maximum, what is phi? Okay, let's ask, what is phi?
Minus times
Phi is minus tangents, tangents t, right? And we know that where is the maximum of phi? At 0.
zero.
So we have to use which formula? A. Right? And what is phi prime?
1 over cosine of
Phi prime at 0.
Sec square?
No, just minus 1.
Minus.
Ah.
Minus.
1 over cosine
Yes.
square.
Minus 1. Minus.
Because of minus.
Yeah.
So we have these two, and we implement A. So what we have is f of 0. What is f? What is f? 1. Okay. So what we have here is f of 0, which is 1, e to the x times phi of 0. What is phi of 0? 0. So this is nothing. And we have phi prime of a, which is minus 1, but we have a minus there. So it's 1 times x. That's 1 over x. That's asymptotics of this integral as x goes to infinity. Okay? Good. Next example. Next example. Integral from 0 to infinity of e to the minus x sinh squared of t dt. Right? Yes. What we are going to do? What is f?
0. 1.
1. Okay. F is 1. What is phi?
Minus h square.
Okay. So where is the maximum of phi?
Also at 0?
Hmm?
At 0?
Where is the maximum of phi?
No. Yes.
That's it.
At 0.
At 0.
Yeah.
Very good.
Yeah.
Okay. So C is 0. Okay. And now, good. So which formula we have to implement?
The first one.
First one?
Yeah, because you have the maximum and the lower limit of the integral.
Okay. So you suggest us to implement this formula because the maximum is in the lower limit.
But you are...
Yeah.
המכנה מתבדר. מכנה אפס.
Hmm?
You are
First
0 is the
derivative.
dominator.
Yes.
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 Why is that? So what's happened?
If you take the derivative
Yes.
of phi with respect to t and plug in 0, you will get 0.
Because, as I told you, this is true. The A formula A is good when this point is a global maximum but not a local maximum. Now, for this it's a local maximum, right? Because sin squared is going like that, right? So close to 0, the minus of this is a local maximum.
So you need C.
So I need C.
And then the factor
I
of
need
F.
C, but
And the factor of F.
good, very good. You see, we need C, but we have to add factor of 1/2 because we have only half. We are integrating on this alone. So what we are doing is we implement C. We are writing 1/2, and now we have to implement C. Now C is square root of 2 pi times f of 0, which is 1, times x to the x. What is phi of 0 is also 0. So this and that are 1, divided by square root of x times the second derivative. What's the second derivative of this? So the simplest way to do that is to understand that close to 0, this goes like minus t squared. So the first derivative is minus 2t, and the second derivative is minus 2. And I have a minus there, so I have 2x. So this square root of 2 with square root of 2 cancels out, and what I have is square root of 1/2 square root of pi over x.
instead of using formula A, you just
I use C.
C.
C and divide it by half. Good. Now, next exercise.
Again, why divided by half?
Because the idea of that led us to C, right, was as follows. We have a maximum, say here. We limit we are saying all the contributions from here, and then we are integrating over Gaussian, right? Now everything is working the same here, except that we are integrating over only on this side, because what's happened is the point A is a point of a local maximum, but it's on the edge, so you don't have another side. Good. Here. Okay, next. Integral from -1 to 1, e to the minus x times sine to the fourth power dt. Good. What is f?
1,
1. What is phi? Minus sine to the 4 of t. Okay. Where is the maximum? The maximum is at 0. Very good. Okay. Which formula should I implement?
This.
What?
D.
D.
But
Why D?
But divide by
No?
no.
Because I am from -1
Yes,
to 1.
yeah,
Second
okay.
derivative.
Second derivative is 0.
Zero also.
Okay?
Maybe also the fourth.
So
Yeah.
what is the first derivative? We know because this is close to 0, this is t
Yeah.
minus t to the 4. So the first derivative is simply 24. Right? So we are going to write now this formula, gamma of 1/4 times 4 factorial to the 1/4. Or what
Would it
it
be
was?
like minus 24?
What?
Shouldn't it be minus 24? Because phi is minus.
No, we didn't.
No, this is that. You're thinking about that.
Yes. And you wrote down.
Wait,
No, we
this
just
is that, this is that,
Okay.
this is 1 again. Now here down here we have 4, that's p, and we have x to the 1/4, and we have phi, this is 24, right? So
Minus.
this is with a minus, right?
Okay,
This is,
okay.
So this is 24 to the 1/4, and they cancel out. So what I have is gamma of 1/4, 1/4 gamma of 1/4 divided by x to the 1/4. And if you remember, this is gamma of 5/4. Because of the recursion relationship of the gamma function. Wait, I did a mistake. Here, there is a 2 here. That I forgot. This 2, so it is okay. Good. Next. Okay. Next. Integral from minus pi over 2 to pi over 2 of t plus 2 times e to the minus x cosine t dt. Yes. Okay. So what is f?
Equals
T plus 0
What is phi?
minus
minus cosine.
Minus cosine t. What is the maximum of phi?
both sides of the same value.
Yes, we have two contributions, right? One of them is at pi over 2, and one of them is at minus pi over 2. Both of them have equal height, so we should add them together, right?
Yes.
Now let's think about one of them, say the left one.
Each of them has one x.
The left one is like having the maximum at A. The right one, this one is like having the maximum at B. But wait, is that right or is that the right thing to do? Because cosine. Yes, cosine is at 0.
Yeah.
Fine. The cosine is 0. It's not a local minimum or local maximum of the cosine, right? So I can use A and B, and so okay. So f of A is what? A is minus pi over 2, right? So we have 2 plus
Minus.
2 minus pi over 2 times, this is 1, divided by x, right, times phi prime at A. Now cosine phi prime is sine, at minus pi over 2 is minus 1, and the minus cancels out. So we have this. Plus the contribution from the other side, that will be 2 plus pi over 2 divided by x. All in all, we have 4 over x. Next. Okay. Now let's speak about cases where I think the simple implementation of the formulas is problematic, and we have to להגדיל את הראש, to think differently. So first of all, the integral from 0 to 1 of sine t times e to the minus x sinh to the 4 of t dt. Right? Okay. What is f?
Sine t
What is phi?
minus sinh to the 4.
Okay. Where is the maximum of phi?
0.
At 0.
Yes.
Okay. Although it's also a local maximum, so we have to, right? However, what is f at this maximum?
0.
0. So if I will try to implement this formula, for example, f of c will be 0. Okay? However, so I cannot implement the formula directly. What I can do is to use the same logic, because what Mr. Laplace told us is that I can first approximate these functions close to 0, and then calculate the integral from 0 to infinity. Okay, so we are not exactly plugging into these equations, but we are using the prescription of Laplace. So what we are doing, we are writing, okay, we know that this will be asymptotic to the integral from 0 to 1 of t e to the minus x t to the fourth. And this is asymptotic to integral from 0 to infinity of t e to the minus x t to the fourth dt. Right?
Yes.
And now to solve this, it's very easy because I will define q as x t to the fourth. So t is q over x to the power of 1/4. So dt is q to the 1/4 minus 1 divided by 4x to the 1/4. And I change the variables in the integral. So I will get integral from 0 to infinity of what? Of t dt is, sorry, this is dq, right? So we have here 1 over 4x to the 1/4, you see, dq. And now we have t. T is q, 2 to the 1/4 minus 1. This is just the dt. You see? Now I have t. T is another q to the 1/4. So this will be q to the 1/2. And this will be x to the 1/2. Okay? And now I have e to the minus q, that's it. Now this is by definition gamma of 1/2. So this gives me gamma of 1/2, which is square root of pi or something, divided by 4 square root of x. So it's 1/4 square root of pi over x. You see? We did not plug it into the Laplace formulas, but we used the same trickery. Okay? And note that the point was that sine t goes to 0. I mean, the f goes to 0 at the point of the maximum, right, at c. F goes to 0 at c. But we were saved because f goes to 0 like a power law. It was not the e to the minus 1 over t that we have considered before. Good. Here is another example, which is the other way around. So instead of considering the case of f goes to 0, let's consider the case where f diverges close to 0. Right? Close to the point. So integral from 0 to infinity of e to the x cosh t divided by the square root of sinh t dt. You see? Am I right? Yes. Cosh t divided by the square root of sinh t dt. So again, we are saying that, wait, should be a minus, right?
Yes.
Should be a minus, of course.
Otherwise, the maximum.
Yes. Okay. So first of all, phi is minus cosh t, and clearly the maximum is at 0. Right? Again, we have a problem because at the maximum, this term diverges. I mean, this sinh t goes to 0, so we have the f of c is infinite. So we cannot plug it into the formula as if it's a nice thing that we can allow ourselves. Instead, we are using Laplace logic. What is Laplace logic? We are saying that this is asymptotic. All the contribution will come from the vicinity of 0. This is still true. So we can write it as the integral from 0 to infinity of e to the minus x times 1 plus t squared over 2, because this is a expansion of Cauchy, divided by square root of t dt. Okay? Now, so we have e to the minus x, and we want to calculate the integral from 0 to infinity of e to the minus xt squared over 2 divided times t to the minus 1/2 dt. And again, to do that, we can use the substitution. So we want q to be now xt squared over 2. So t is 2q over x to the power of 1/2. And therefore, dt is what? Is 2 square root of 2 over x times q to the 1/2 minus 1 times, no, because I have to divide by 1/2 because of the derivative of the q.
Yes, and the q.
Okay?
The q.
The q. So I have e to the minus x integral from 0 to infinity, e to the minus q. Now this, okay, and now we have here, we have square root of 1 over 2x, right? And now we have q to the 1/2 minus 1 dq, but we have also the t to the minus 1/2. T to the minus 1/2 is t to the minus 1/2 is 2q over x to the minus 1/4.
Yes.
Am I right?
Yes.
Okay. So we have q to the minus 1/4. So this will be 1/4. And we have 2 over, and we have here x over 2 to the 1/4. And what else? That's it. You agree?
Yes.
Now, this is gamma of 1/4. So the final answer will be, if we didn't make a mistake, the final answer will be 1 over, okay, we have e to the minus x, gamma of 1/4, right? And we have x to the 1/4 down here, because this is x to the 1/4 divided by the square root of x. And we have
2 to the 3
2 to the 3
over 4.
fourths. Right, let's check. Yes. Okay. Okay? Good. So these were two examples in which f of t either diverges at 0 or explodes at 0. Now it's not the divergence and the explosion are still power laws. And because of that we can, although we cannot use the formulas, we can use the logic of the formula. Okay? Now, the last, no, we still have some time. Let's now make an example in which we have a problem with the moving maximum, like the one I've showed you, right? And this is a nice example. I want to calculate my integral that I want to approximate is the integral from 0 to infinity of t to the x minus 1 e to the minus t dt. Now what is that? What the hell is that? Gamma function of x, right? So I want the asymptotics of the gamma function at large x. Do you know what is the asymptotics of the gamma function? Sterling, exactly. So now we want to find Sterling. This is our goal. Okay? Now, so I can write that as the integral from 0 to infinity of e to the minus t plus plus x, let me, plus x ln t divided by t. Do you agree with me? Okay? So my f now, oh no, sorry. Now, where is the max? So my phi is minus t plus x ln t. Of course, I cannot implement, okay, I shouldn't write that, right? Because writing that, phi will be ln t. So it's something. If I am taking this naively as a Laplace integral, right, I will take phi to be ln t, right? And then I will ask, where is the maximum? The answer is at infinity. Good. The maximum is at infinity. So I will go to infinity, and I will find out that I have here e to the minus t that kills the contribution, right? So I have to be more careful and to find out where actually is the maximum, and to do that I have to implement the method of moving maximum. Okay? So now I will I see that I have e to the x ln t minus t. So let's look at this form, at this term. Where is the maximum of this term? Where is t
1 over x.
star? T star, I have x over t minus 1 is 0, so t star is at x.
Oh, okay.
The larger x is, the farther away my maximum is. Because you see the way it looks like, right, it is going exponentially, but then the e to the minus t is taking me down. And this is 1 over x.
X, not one.
X. So this is x. Okay? And as we did before, what we want to do is to define new variable that I called, in the former lecture I called
G.
z.
G. Oh.
No, not g. G was a function.
Yes, that's it.
Z.
Something like
So z is t over t star, which is, in our case,
T over X.
t over x. Okay. And now I want to change the integration, to change variables in the integration. Right? So what I have? Z is t over x, so t is zx, and dt is x dz. So I have the integral from 0 to infinity on 1 over t, which is 1 over x times, and I have z here, right? Okay? And in the exponent, I have e to the minus x times z plus x times ln t. But t is zx. So I have x ln z plus x ln x. Because ln t is ln xz. Do you agree?
Yes.
Good. So I have e to the x ln x divided by x. I don't like this x, but let's hope that it is good. Integral from 0 to infinity of e to the minus x
Wait, you forgot the dt.
d
Replace the dt.
dz.
Yeah, but you have.
Ah, yes, and this is why I don't have an x here, because the dz over z
Yes.
kills the Jacobian. Yes, okay, fine. Okay, so I have e to the minus,
remove the
I should remove the x here.
Nice.
Thank you.
Nice and clear.
I told you I don't like this x. Okay,
We need that.
and now I have e to the minus x times what?
Z plus lambda.
Times, no, I have a minus. Times ln z minus z. If I have a minus, so it's z minus ln z divided by z. dz.
So you can take the z minus, you can take the z ln z as
Now I'm doing Laplace integral.
Yes.
So my phi is z minus ln z. Phi prime is 1 minus 1 over z. Right? And phi double prime is
1 over z squared.
1 over z
1 over
squared.
z
1 over z. Okay?
squared. Z equals
So,
the max.
C, z equals 1 is z star equals 1, is where the maximum is.
Minimum.
Whatever. Is a point that in which I want to take the integral. And phi of 1 is what?
1.
Is 1.
with one.
Because ln 1 is 0.
And
And
phi
phi double prime
Equals
of 1
also 1.
is also one.
is also 1. Okay? So what I have here is e to the x ln x. And now I have
C, the equation C.
e to the, okay, and now I am expanding that, okay. I have e to the minus x. You see, this is
Yes.
e to the x phi of c. Now, f of c
Also 1.
is
1.
It's one.
y
It's one
is
over
1,
one.
f
One
is
over
1 over z.
Yes, it's
Yeah.
1 over 1.
F of c is 1, yes.
Square root of 2 pi
I have square root of 2 pi,
over
and then I have to divide
square root of x.
by square root of x times the second derivative, which is 1. That's it. So this is the leading expansion in Stirling formula. So it is actually gamma of x is asymptotic to at large x to square root of 2 pi over x, right? Times x to the x, because e to the x ln x is x to the x, e to the minus x.
X ln x minus x is not a gamma x by the Stirling approximation.
Yeah, this is Stirling approximation. This is Stirling formula. Let me just make sure that I did it right and didn't miss something here. Yes, that's the Stirling formula. Yes, for the gamma function. Of course, what confusing is that gamma of n is n minus 1 factorial. So if you want to use it for as a way to calculate factorial, you have to subtract, add 1 to x or something. But essentially this is the Stirling formula, and you can use it, you know, it's very popular. Okay. Fine. So I just want to okay. So what we have in the exercises now, we actually surveyed 3 situations. Situation number 1, when f of c was finite at c, then no problem. Just plug it into the formula. There is nothing else. except of, you know, making sure that you took all the global maxima in the region, because maybe there are two. Make sure that you are using, if it's local, if it's not a local maxima, you use here, global maxima you use here, and factor of 1/2 and so on. Right? This is one class of uses. Another class is when f of c is either diverging or going to 0 at c, in which case you cannot use this formula that way, but you can use the logic of the formula. Expand everything around c, and then expand the domain of integration to infinity. The other situation is when f of c is going to either to 0 or to infinity exponentially fast. So it is going like e to the minus 1 over t close to 0, or like e to the t at infinity. In that case, you cannot implement the logic, because it's you don't have, I mean, if you think about it in terms of the the Watson lemma, you don't have power law expansion of any kind to f of t. Instead, what you're doing, you are using the moving, you're doing a change of variables and implement the Laplace method, not to the maximum of phi per se, but to the moving maximum. Okay? That's it. So this is how we implement Laplace integrals. Okay? Now, I didn't notice, I've noticed that only during the break. So what we did was we showed a few ways to approximate integrals, and I already sneaked the two-time perturbation theory, such that it will not be, you know, the material of the last lecture, because this is something that students hate. Still, okay, I'm still feeling, and so next time I will mainly devote the lecture to exercises about the two-time perturbation theory. There is still one point about integrals that maybe I will add, which are Fourier integrals. So Fourier integrals is like Laplace integrals, but okay, the only difference. No. Complex is what they call the, I told you, complex is what they call the steepest descent. And this is something that I'm not going to, I have no time, I have to make a choice. That's my choice. There is something like that. Purely imaginary, right? But you put something like that. This is Fourier integral. And you want to evaluate it when x goes to infinity. Now, the point is, well, the important point is that as x goes to infinity, every integral of this kind is going to 0. This is, what's the name of this theorem? Riemann-Lebesgue? No. Riemann somebody. Listen here. Riemann-Lebesgue, yes. Riemann-Lebesgue theorem tells you that this integral goes to 0, as x goes to 0, this integral is going to 0. Why?
To infinity, no?
As x goes to infinity.
As x goes, as x goes to infinity, of course, I goes to 0. Why is it?
Because firstly,
Of course, yes. Because think about the real part or the imaginary part, right? You have some f of t, right? You want to integrate over f of t. So f of t, let's assume that it is something like that, I don't know, something that has an integral. But now you multiply it by cosine or by the sine of x times something. And how this cosine is doing, what this cosine or sine of x times something is doing with x equal to infinity it is doing something like that. It has infinite oscillation, and it simply cut the red line into two, and create an imaginary thing here, and it averages to 0. Right? So the Riemann-Lebesgue theorem tells you that every such an integral is going to 0 as x goes to infinity. Okay? The only question is how fast it is going to 0. And now the trick is that what will be the regions in this integral that will give you the largest contribution?
The minimum of 5.
Doesn't matter. If phi prime is 0, no matter if it's, what does it mean? It means that the changes of the cosine, the cosine is doing, ups and down, ups and down. You have in a frequency that is x times phi. So when phi prime is 0, the changes of the argument of the cosine are the slowest. Right? So relatively, if phi prime goes to 0, say here, so instead of doing like that, it will do like that. It is still going up and down, but at a different pace. And for that reason, the main contribution will come from the places where phi prime equals 0. Right? And this is actually it actually leads you to very similar, although it's completely different because you don't have something that is growing exponentially or decaying exponentially, but something that oscillates. Because of this phenomenon, still the main contribution will come from the point where phi prime equals 0. Not because it's minimum or maximum, just because, and you don't care if it's a minimum or maximum, just because it fluctuates less rapidly at the vicinity of this point.
But how can it be? I can just plug like yx equal to y to the plus.
Okay,
What changed?
maybe I will say something about that. Maybe I'll spend about it like half an hour next week. It's worth doing because this is essentially quantum physics. This is, what is that? These are interference, right? You have interference of many possible paths, right? And x is like h bar. So as h bar goes to 0, you have only destructive interference and it kills the amplitude. But at the point where phi prime is 0, you get contribution. And this is actually how classical physics emerges from quantum mechanics that way, right? You get contributions. Phi is actually the is the Lagrangian, right? So this is h bar, and this is the action. The integral over this is the action, and the point is that when h bar goes to 0, you get contribution only from places where the action is the extremum, and these are the classical trajectories, right? So just general background, but there is something, at least the first part is very simple. So I think that next week I will spend like half an hour on that, and then we will move to the exercises. And if I will not have time, so at least you know now that there is. Right? Okay.
Thank you.
Wait. I have to. Yes. My charger. In any case, it can stay. I have enough in my office.
השיטה הזאת, אתה יכול להשתמש בה כדי לחשב גם את התוצאה של האינטגרל האקספוננציאלי?
מה, האקספוננציאל אינטגרל שהראיתי בפעם הקודמת?
כן.
אנחנו מצאנו אותו חוץ מאשר את המקדמים. אפשר למצוא אותו בקלות. המקדמים זה לא עבודה קלה. לא חושב שזה בא מפה, אולי כן, אבל זה לא חושב על זה.
הולכים לאכול?
אנחנו עוד בעיכוב על השיעורי בית. אם הוא לא מעלה שיעורי בית, לא צריך אם הוא לא מעלה שיעורי בית, לא צריך להזכיר לו.
זה מה שאני אומר, בגלל זה שיהיה בשקט. בטוח, אפשר לדבר על השם.